Well, I guess in the interest of time, we'll go ahead and start. Happy Friday, everybody. Thank you so much for tuning in today. I'm excited to introduce our seminar speaker this week, Dr. Masatoshi Hirabayashi, who is currently an assistant professor at Auburn University in Alabama. He's actually just a short drive away. We were just talking about that. It's just 2 hours away. So hopefully he'll be able to visit in person. And so definitely keep that in mind if you're interested in any of the work that he's going to be presenting on today. He's a planetary scientist and engineer whose research has focused on studying small bodies and their volatiles in our solar system, like asteroids, although he also does work on the moon and has also focused on technology development. He received his bachelor's in aerospace engineering from Nagoya University, a master's in aeronautics and astronautics from the University of Tokyo, and then a PhD in aerospace engineering from the University of Colorado at Boulder in 2014. He then did his postdoctoral work at Purdue University, where he was there for about 2 years. And then in 2017, he started the position that he currently has at Auburn. And so thank you, Toshi, for talking with us today. And if there's anything that I missed about your background, feel free to share a little bit more with us. But thank you again, and take it away.
Thank you, Francis. First of all, I really thank all of you to be here, and I'm so excited to have this presentation. So my name is Toshi Hirabayashi from Auburn. I am assistant professor in aerospace engineering, and I also have an adjunct appointment in geosciences. Auburn is located really close to Georgia Tech. It's like few hours by drive. So I'm hoping that there gonna be opportunity that I can visit you or I can host you to be here. So I'm hoping to have a lot of active discussions with you. Okay, so today I am going to introduce the roles of small bodies in habitability. Particularly, my expertise is dynamics and structure, mainly targeting small bodies and the moon and other bodies. So applying those, I try to explore this question. Okay, here you go. So regarding the interactions of small bodies with other planets, this is a very critical point because when you consider the evolution, yes.
Excuse me. At least on my side, I don't see your slides anymore. Can somebody
Really?
else
Okay.
confirm if that's
Maybe
the
like
case?
yeah,
That's
just a
true.
second.
Yes. I can't see.
Thank you. Thank you for letting me know. So let me just one more time. Can you see that?
Perfect.
Okay, thank you. Okay, so when it comes to the interactions of small bodies, like I said, it is very important because when you have gravity perturbation from large planets like terrestrial bodies or gas giants, you'd be able to be perturbed over the life of the solar system. So when you have small bodies, like in the outer solar system, they eventually come down to the inner solar system. Eventually, they arrive around the region of the around the Earth-Moon system. Important part is that some of them contain volatiles, hydrated minerals, and organic materials. Those are one of the key items for life. So these small bodies are actually the carrier of these key items, key materials to the Earth, Moon system, and other inner solar system bodies. At the same time, I want to mention that, okay, like I said, the small bodies are actually the suppliers of those materials. At the same time, when they supply these materials, they destroy the existing habitable environment. So the idea is that there is some like ecosystem of balancing between supplying these materials and destroying existing environment. So the key question is that how the small body transport mechanism contributed to the Earth-Moon system. This is one of the questions that I'd like to, or we would like to answer by using theoretical and numerical approach, as well as taking into account spaceflight data and observation data. In this talk, I specifically want to discuss 3 different questions. First one, how does a small body that closely approaches the Earth-Moon system behave structurally? Number 2, how do volatiles exist and evolve at the lunar polar regions over the corrosional history? And then how do most common asteroids exist in the near-Earth region and influence the Earth-Moon system? For the third question, I do not discuss how we approach this question by analysis, but I want to introduce currently ongoing spacecraft mission design, and I'd like to show how this mission is going to answer this question. So I'm going to discuss these 3 questions, starting from the first one. How does a small body that closely approaches the Earth-Moon system behave structurally? There is a great opportunity for us to investigate or test this question. Apophis is an S-type asteroid approaching 6 Earth radii away from the planet's center in 2029. The closest approach occurs on April 13th. The right figure shows the trajectory of Apophis passing the Earth, which is giving its disk here, circle here. Asteroid is about 200 meters in diameter. It is a non-principal rotator. Also, recently, radar observations created the shape model. The project was led by Marina Brozovic. So the shape is very interesting because the body is elongated, and if you look at it closely around this area, if you look at the cursor, there is some neck region. So this is technically not a spherical nor just a elongated shape. It has a complex shape. So our approach here, in order to answer the question, we explored how the stress condition evolves during the closest approach and how the shape affects the stress distribution. We considered this question or this approach by using our FVM modeling. Apophis internal condition is very critical, particularly when you consider the closest approach, because when you look at the closest approach, the tidal effect is dominant. So it is necessary to understand the behavior under the tidal effect. Key issue here is that numerical work demonstrated that the spin state changes dramatically during the 2029 closest encounter due to the tidal torque. However, observations have not yet constrained the gravitational state well, given the close observational resolution. Also, although I mentioned that there exists a radar shape model, there are still uncertainties of the detailed topographic feature, particularly higher resolution. Given this, our consideration right now is that how we can quantify the behavior of internal structure or response of internal structure to tidal effect, given these uncertainties. So we decided to conduct sort of like Monte Carlo simulations by using our FEM model. How did we do it? We considered uncertainty of rotational condition. I'm showing here the table on the right. This is a spin condition identified at an epoch of December 23rd, 2022. As you can see, precession, average rotation, and rotation, those are having higher uncertainties. We considered in order to characterize these uncertainties, it is useful to characterize a different spin condition for each parameter. So for this case, we considered 6 different cases for each rotational parameters here to conduct in total of 216 cases. So we propagated all these spin states from this epoch to 7 p.m. on April 13th, 2029, which is 2 hours away or 2 hours before the closest encounter. Also, we computed the initial stress condition, which is identical to the time of this epoch, by considering a static equilibrium state of the body. Given these items, we ran FEM simulations to understand dynamic and structural evolutions over 5 hours during the encounter. So starting from 5 p.m. to the midnight on April 14th. So around 2 hours and a half, around that time, the body should encounter the body should experience the closest encounter. Okay, so like I said, we had 216 cases in our simulation. And then I would like to introduce just 2 of them as an example. So here, the red arrow shows the line of sight direction toward the Earth, and the blue arrow shows angular velocity orientation. The color bar shows dP. This is a pressure difference relative to the initial condition, by which I mean 7 p.m. To our 7 p.m. on April 13th. As you can see, the scale of the color bar here, it's small. The units are pascals, so you anticipate the pressure difference is very low, but you'd be able to see the variation during the closest encounter. So let me start the video here. Around 170 minutes, you'd be able to see the higher negative pressure difference here, and then it's gone. This is because the asteroid passed the Earth. I'd like to show the different case 2. For this case, the red arrow is pointing different direction, and I'd like you to see the neck area. As you can see, when you look at around this region, now you have a positive pressure difference. And then after 170 minutes, it's gone. And then now you have the blue region and it faded away. This is because the asteroid passed the Earth, right? So by this, we are observing that rotational state is very important to control the pressure difference. Based on these videos, I would like to discuss the magnitude of stress difference statistically. So I'm showing here on the left, this is pressure difference and absolute value of pressure difference. And the right side shows square root of J2 difference. By square root of J2, this means a shear. So this means a shear difference. The dotted line on both plots are showing upper bound, and solid lines are showing lower bound. And dashed dotted lines are showing the mean value. So as you can see, there is a peak around 2 hours and around 30-40 minutes. This region is exactly the closest encounter. So the stress level reaches the peak when the body reaches the closest position to the Earth. The value here is technically low. The value of pressure difference is around 0.3 pascals. If you look at the shear difference, it is around 0.45 pascals. So it's very small. I'd like to show where exactly that stress peak happens. In order to do so, we considered the frequency over the entire cases. So we considered 216 cases. And then how many times each area, each tile experiences stress level higher than 0.05 pascals. The top row shows shear difference, and then lower row shows pressure difference. If you look at the shear difference, you can see that the frequency is around 0.4. Around 0.4, 40% of the cases experiences these stress level around the neck. It is widely distributed, but we can observe that, okay, neck region is the one experiencing higher stress variation. If you consider pressure difference, the situation is more obvious when you look at panel C. There is a higher frequency around the neck. This region corresponds to convex region, so we can imagine that, concave region. So we can imagine that experience sort of like stress concentration, although the magnitude again is low. From this analysis, we found that regardless of the spin states, the neck area is a sensitive region no matter what you have stress condition. But variation itself, the magnitude of the stress variation itself is low. So the summary for question 1 is that Apophis closest encounter in 2029 is a very useful or important opportunity to test how asteroids behave due to closest encounter. We investigated this condition or this opportunity by applying FEM to investigate the internal evolution of Apophis. We found that the rotational evolution and tidal effect causes the stress field variation up to around 0.5 pascals. And then the value itself is not that high, but we found the critical point that regardless of the spin state during the encounter, neck region is one of the most critical region to have variation, high variation compared to other region. Okay, so regarding question 2, this is focusing on volatile distributions on the moon. When it comes to the volatiles on the moon, we now know that the polar regions host volatiles, particularly within permanently shadowed regions. There are several potential processes delivering volatiles from outside or inside. So first one may be impact cratering. Next one is volatile volcanic activities. And the last one would be solar wind. The key question I'd like to address here is that, okay, when you have delivery of volatiles, then you should have additional processes to redistribute them. The idea is Moon has been experiencing a lot of different bombardment histories. Bombardment processes. In this case, it is possible that these processes, impact processes, could redistribute volatiles. So the idea is how impact processes could have contributed to the current distribution of volatiles. Particularly, I'd like to discuss here the water ice. In order to do so, we employed a statistical approach to analyze material mixing depth or material mixing levels in local areas. So for analytical model, this computes material mixing by tracking the total number of emplaced craters. I'd like to introduce how this works. So the left figure shows the crater surface. We are looking at this surface from the top. The right figure shows exactly the same surface, but we are looking at it from horizontal direction. So also the disk orange circle is a newly emplaced crater, and then yellow one is old crater. When you consider younger surface, there are just a few craters. So statistically, when you have a new crater, then this crater is unlikely to overlap with old craters. So the generation of mixing may not correlate each other. However, when you have more craters, then the situation is different because existing mixing zone could be affected, affecting newly emplaced crater region. This is because it is likely that this new crater is emplaced on the existing craters. In reality, we also have to consider the size distribution. For example, if you consider large craters, then mixing zone would be large, but if you consider smaller one, then mixing zone would be small. So we need to consider these variations. The analytical model can take into account these effects statistically in order to characterize the distribution of mixing area. We applied this technique to 3 complex craters located around lunar south polar regions, Haworth, Shoemaker, and Faustini. First of all, because we need to get the total number of emplaced craters, we calculated or we computed cumulative size frequency distributions by counting craters inside of each crater. We used the LoRa DEM model, and we developed CSFD for the crater of these craters. And then our model age or derived model ages were consistent with earlier work by Deutsch et al. And Tai et al. So we used CSFDs for these craters to calculate the mixing depth. So the left side shows the CSFD plot for all the craters as a function of diameter. And then if you look at the dashed line, those are the production functions developed based on Neumann production function. Using these production functions, we calculated the mixing depth distribution as a function of depth. Here, I specifically using area fraction. So the area fraction is a ratio of mixed area at the depth over total area. I'd like to give example in order to visualize what this means. So let's consider this blue or purple solid line right here as an example. So let's take 50% of area fraction. So if you go through the depth, eventually it intersects with a purple line here at depth of 10 meters. So by this, we can read this point as 50% of area. 50% of area is mixed at depth of 10 meters. By this I mean technically we are looking at the area fraction at a given depth, like how much mixing occurs. This is what area fraction means. So the solid line is upper bound and dashed line shows the lower bound of area fraction. So the shaded region between them is potentially the reasonable area fraction distribution of each crater. If you have, or if crater is older, then this shaded region push to the right side. So Haworth and Shoemaker are older than Faustini. So those are having a higher area fraction at a given depth. We also computed the mixing depth distribution by considering local area. So local area was defined by using different grid sizes. Here I am showing 3 different grid sizes. Largest one is 7.5 kilometers. Next one is 5 kilometers. And then last one is 2.5 kilometers. Here I am showing, okay, so when it comes to large grid and medium grid, those are fairly consistent. By consistent, I mean when you look at these 2 different grid sizes, you would be able to see the consistency or reasonable matching of mixing depth. For example, for Faustini, we can see similar trend. I have to mention that although we considered or we saw some consistencies, we had some exceptions, particularly those anomalies. Panel A and panel E, those are giving some high mixing depth region. However, by ignoring these anomalies, we considered these plots are consistent, and then we observe that local regions are actually different, or mixing depth at the local level is heterogeneous even if you consider the same crater floor. So if you consider Faustini, you have some distribution of mixing depth over the entire floor. By this, I mean it is necessary to consider this type of heterogeneous distribution. Otherwise, we're gonna lose key information over the history of the floor in terms of the impact bombardment. If you consider a small grid, then the situation was different. So I would like to consider this one is not giving any critical information. The reason was that when we try to make a smaller grid, we needed to ignore those large craters, which are a critical contributor for mixing depth. And then because of this issue, we confirmed that when you have a smaller grids, we could not reproduce similar trends as we saw in large grid and medium grid cases. So we did not consider this one. So based on that, now we would like to compare our results with observed water ice distributions, particularly at a top surface, the thickness of about a few microns. I am using data from Lee et al., who use M-cubed data. So the figure at the center shows the distribution of detected water ice distribution. We would like to compare this distribution with the predicted mixing depth. So the idea is how we can convert our predicted mixing depth to proper data or information for water ice concentration. So I'd like to discuss here the schematic at the center. So given the hypothesis we considered or that have been discussed before, major processes are actually delivering water molecules outside the crater. So water molecules are not coming from the inside of the floor, but they're coming from outside of the crater. By this, I mean initial process is likely the accumulation of these molecules at the top of the surface. So given this idea is that you'd be able to imagine initial condition may have a higher concentration of water. However, as time goes, the impact processes mix the top surface, and then that mixes water ice as well. So it is gradually making the concentration lower. Given this idea, our model actually implies that if you have a shallower mixing depth, then this implies that water concentration may be high. So if you have consistent, or if the predicted shallower mixing depth region is consistent with detected water ice distribution, then we can consider that impact processes would be one of the key processes to control the water ice distribution. Given this idea, let's look at the left figure. So I am showing here the figure, the distribution of detected water ice distribution on the predicted mixing depth. So if you look at the correlation between them, what we see here is, okay, no correlation. Even if you look at panel A, higher anomaly region, so it is around like 12 meters. We anticipated these regions should not have high water ice concentration. However, top surface should have it based on Lee et al.'s data. This means that there is no correlation between mixing depth and or impact-driven mixing and existing water ice distribution. This is critical because the idea is this result or this study is proposing that there exists another process that could be transporting water ice rapidly, much shorter than geologic processes of impact events. So this idea is very important because when it comes to the future lunar exploration mission targeting water ice, where exactly water ice exists, I believe that this information will be able to constrain potential sampling site. So this is a summary for question 2. I explored the rich distribution of water ice driven by impact processes around the lunar South Pole. We applied a statistical approach to characterize the mixing distribution on the crater floor. We also compared the shallow mixing depth distribution and the water ice distribution at a top surface at a few micron. And then we found no correlation between them. By this, I mean there exists a rapid process that can reverse and redistribute water ice. I do not mention what kind of processes is actually contributing to do it, but I am proposing that impact processes are not part of it. This is the conclusion of this analysis. Finally, I would like to introduce this question. How do most common asteroids exist in near-Earth region around and influence the Earth-Moon system? Here, instead of directly answering this question, I would like to introduce our efforts in developing a new exploration mission. Before introducing what exploration mission that I want to discuss, I introduce the background. So when you look at the distribution of spin periods of small bodies as a function of diameter, we see very interesting features. So there is a boundary around 200 meters in diameter. If you look at larger small bodies, there is a clear border of the spin period, which is around 2 hours. This is what we call the spin barrier. By this, we consider that these asteroids cannot spin faster than 2 hours. This implies that these small bodies likely be a rubble pile bodies. On the other hand, if you consider smaller bodies right here, they can spin faster. By this, we can imagine that they could be monolithic or rubble piles with cohesion. When it comes to the exploration in the past targeting small bodies, there are very interesting trends. All the spacecraft missions targeted larger bodies. However, when you look at those smaller ones, we now know that those are the most common object in the inner solar system. This is because you can imagine smaller ones, the more, when you consider smaller bodies, the population would be high. However, when you consider the properties, physical properties of these bodies, we really don't know what exactly they are. The reason is it is very hard to observe them from by using ground telescope and even space telescopes. So we are having very critical challenges to identify what exactly they are. So it is necessary to visit them and observe them in situ. PSAS 2 mission is the Japanese asteroid sample return mission. This mission successfully conducted 2 touchdown operations and 1 impact experiment. So the movie right here is showing a successful touchdown on the target of asteroid Ryugu. In 2020, the spacecraft came back to the Earth and released its return capsule. And then we captured the fireball event of the capsule while entering the atmosphere. So, HIVESA-2 extended the mission, which is what I want to discuss now. This is a small body rendezvous mission that uses the already flying HIVESA-2 spacecraft. The spacecraft is currently flying without no critical issues. The extended mission explores two key items. First one is scientific advances in the inner solar system evolution and planetary defense, and engineering technologies for extremely long-term explorations. Mission just started and is planned to continue until early 2030s. Key part is that Auburn contributed to develop this mission entirely, starting from mission calculation and writing proposal, and I'm really glad that the mission was approved. So it's gonna start, or it's already started, and see how it goes. Regarding the rendezvous target, this is 1998 KY26. The asteroid is spheroidal, and equivalent diameter is around 30 meters. The spin period is around 10 minutes, which is really quick. Tumbling mode has not been observed yet. Potential material compositions are reported to be carbonaceous and hydrated minerals. Because of the fast spin, this asteroid is expected to have unique geophysical, geomorphological features. When it comes to the internal structure, there is clear tensile conditions. When we calculated the stress field inside of this asteroid, we observed that normal stress is up to 5 pascals. So this is definitely tension. However, the scale of stress is very low. This is almost comparable to the cohesive strength of other rubble pile asteroids. So potential idea here is that yes, this asteroid could be monolithic because centrifugal force is dominant, but there is still opportunity or possibility that this asteroid may be rubble pile. Loose materials cannot exist in surface regions unless there is a cohesion. However, if there exist such materials, then we can consider that, okay, there exist additional attractive forces. Fractures, craters, and other geomorphological features correlated with the asteroid's evolution. So it is very exciting to see what kind of features existing on the surface. There are 5 phases in this mission. Phase 1 was already completed, which was the Earth swing by in 2020. Phase 2 is to flyby 2001 CC21. This is another asteroid. We're going to conduct remote sensing observations during fast flyby operations. Phase 3 is Earth swing by in 2027, and the phase 4 is last Earth swing by in 2028. After that, it goes to KY26 directly and conduct proximity operation. During this long-term cruise, we also plan to observe zodiacal light and exoplanets. So I didn't mention about how we investigated this question, but I introduced how we tackle this question by proposing spacecraft mission. So JAXA Hayabusa 2 extended mission was developed and just started its operation and continues until 2030s. Target will be 1998 KY26 and 2001 CC21. The mission will explore the following questions. How do the most common astro objects look like? What would the transport cycle be? And how have such objects influenced the surfaces of the Earth-Moon system? So we are really thrilled to see KY26 in 2031. Okay, so this is a summary of the entire talk. So I try to describe the answers, partial answers to the question and approaches to answer these questions. So the first question we considered PAFIS, which is coming to the Earth in 2029, and it is likely to have some effect or gonna experience tidal effects, and it will have some evolution of internal structure. We observed that the stress level or stress variation level will be low, but we observed that the neck regions would be one of the highest sensitive regions over the entire body. For the next question, we investigated the volatile redistribution processes around the lunar poles. We investigated how impact processes contributed to the redistribution of volatiles, and then we found that it is necessary to consider the heterogeneity of mixing depth distribution, even in crater floor of one complex crater. When we considered when we compared our mixing depth distribution and observed water ice distribution at the top layer, we had no correlation between them. By this I mean water ice is actually transported by other process in a short time period. Finally, regarding question 3, we designed and developed a spacecraft mission which is currently ongoing, and hopefully it will arrive at KY26, and we'll see how it goes. By this, I'd like to end my talk, and I'll take questions. Thank you. Thank you.